Great, hi everyone. Thanks for coming. So today we'll be talking about cloud and Kubernetes. We have a few live demos. Hopefully they go a little bit better than the talk before. Okay, I cannot do next. Okay, good. To set the stage a little bit, we are in the cloud, so we are using managed Kubernetes clusters. We have applications running on it. And we want to look at what happens when an attacker wants to exploit our application. What they typically want to do is to pivot, right? They want to go from the application to the cluster, to the cloud, and back and forth. So that's a bit the context that we will have today. I'm Christophe. I work at Datadog, focusing on cloud security and open source. We are a company based in New York, but also in Paris, and I'm remote in Sweden. So these are the three main managed Kubernetes platforms, right? EKS. Who's using EKS in AWS here in production? A few people. GKE as well. AKS on Azure. A few people. So we'll focus mostly on EKS, but it should be applicable to all the three clouds, and we'll have some recommendations for the three. And again, what we're going to cover today is we have an attacker, they can compromise one of our applications. What can they do from there, and how can we make sure that the impact remains very small? The first scenario that we'll see is what if they are able to run arbitrary commands, which obviously is the worst, right? If they can exploit something like log4shell. What if they can trick your application into calling arbitrary URLs, which is a kind of vulnerability called server-side request forgeries? And finally, what if they can leak just a single file from the file system? A bit of introduction before of what is called the instance metadata service. So it's something that's specific to cloud environments, but it's very relevant to Kubernetes in these environments. So when you have cloud-native applications, they typically need access to cloud resources, right? You have your virtual machine, they need to access S3 buckets, things like that. So typically the way you grant them access, and that's applicable to AWS but also others, is you assign a role to your VM, to your workload, and then it can automatically get some credentials through something that's called the instance metadata service, which is listening on a link local IP through an HTTP request. So by design, anything on that machine can hit the instance metadata service and get back some credentials. It feels a bit like magic, but in reality, when you use that, you don't see it because it's handled transparently by the SDKs, by the AWS CLIs, things like that. So this is for AWS, but in Azure, GCP is the same. And really the goal is to provide workloads with a platform identity that they can get automatically, transparently, with some temporary credentials. Now, in the context of managed Kubernetes, so this is for EKS, but it's the same for others, you have worker nodes, right? You have your control plane managed by the provider, and you have your worker nodes, and they need to do different things. So when you run your pod, they need to be able to pull the container images, to create network interfaces, things like that. So you need to assign them a specific role. And the issue, as we saw before, is that any process on the host can call the instance metadata service to get the host cloud credentials, which means for us that any container as well can retrieve cloud credentials for the host, which most of the time is not what you want and is not really intended. So now we know what it is, how can we abuse that? And again, the root cause of the problem here is that our pods can, by default, very often access the instance metadata service and steal some credentials for the host, which is not what you want. So if we are an attacker and we try to exploit the application that runs in a pod, there are different ways that we can try to get these credentials. The first one is remote code execution, right? If your application is vulnerable to that, I can just curl the IMDS and get back some credentials. If I can exploit a server-side request forgery, same, I can trick the application into calling it for me, and we'll see that in a bit. So first example, very simple. This is a vulnerable application. I can give it a domain name, and it's going to ping it. Unfortunately, it was written in Java, so it's slightly vulnerable, so I can pass the end ID command. It executes it and gives me the output. So what I can do is just, as I said before, curl the instance metadata service, and I can say here that I can call it. And we'll see in a bit how to exploit that. Now, server-side request forgery, who has ever heard of this name, which sounds very scary? Okay, almost everyone. So interestingly enough, it has its own OWASP top 10 entry, but only since 2021, showing that it's getting more and more popular. And it's very common. So if you look for SSRF in Google for HackerOne public reports, you will see around 460 results, which is quite a lot, including in the Department of Defense and different companies. So it's very widespread. And the idea is really that as an attacker, you can provide an untrusted URL to this web application and trick it into calling it for you, which in the context of the cloud, but also specifically of EKS, it means that as the attacker, I can trick the application into calling the IMDS for me and stealing back some credentials for the worker nodes in the cloud environment. And then the attacker is happy. So, quick demo. We have here this sample web application that's vulnerable to a server-side request forgery. So I can call any URL, including 169.254. And I can just do latest metadata IAM security credentials. This will give me the name of the role that's attached to the worker node. Up. I can just append that, and I'm getting back some cloud credentials. So now, what do I do from there? I can just put that into a JSON file, and I will just put that in my environment variables. So this is just the way that, as the attacker, I stole the cloud credentials, and I can authenticate to AWS with these. And now I can do get caller identity, which in AWS gives me basically my who am I, and we see that I'm now authenticated from my laptop as the worker node of the cluster. So next question is, what do we do from there? And again, the goal is to pivot, right? Now I compromise the single cloud role, which is the one of the worker node. What do I do next? So the role that's attached to the worker nodes in EKS has some permissions which are not privileged, but still interesting. First one that you see on the left is the ability to describe, to list all the EC2 instances, all the networking configuration, all the clusters. So it's already quite interesting for an attacker. This one is going to help you pull all the container image from the account. And this one is going to allow you to delete all the network interfaces, which is not great. So pulling container images is super interesting for an attacker. Why? Because, well, these are where your applications live. So if, as an attacker, I can pull that, it means that I can read the source code, find other vulnerabilities, and actually find secrets very often. This is a paper from a few months ago where they found that around 8% of images had secrets. So if we continue our exploitation here, as we saw, I can describe EC2 instances in the account, which gives me an idea of how many there are. Is it worth putting more time into it? Then I can do ECR up. Let's see all the container images available here. So we have one that's called the domain tester service. So let's try to pull it. And for that, I need to authenticate to this private registry. The way this is done is just with this command, where you generate a token with the AWS CLI and you pipe it to the Docker login command. Very standard, this is in the docs. Then I can just pull it, which I have done already because it's a conference Wi-Fi. And then once it's on my machine, I can just try to run it, right, and find I know what is there in this container. In this case, I can see that there are some AWS credentials hard-coded in there, which would allow me to do further things. That's the easy case, but in many cases, it's a bit harder, right? So for instance, in that case, there's also another thing, which is if you do Docker history on the layers of this image, it shows that someone tried to do a multi-stage build with build arguments, but actually these credentials still end up in the layers. So that's just some examples of things that you can do as an attacker, having compromised an initial role of a worker node. Now, that was for EKS, so I just want to show a little bit the difference with other clouds. In Google Cloud, nodes use something that's called the default compute service account with a limited scope, which essentially means they can read all GCS buckets and all BigQuery datasets in the project, which is quite worse. But it's actually harder to exploit because you need, when you call the IMDS, you need to give a specific header. And when you exploit a server-side request forgery, typically you don't control the headers that the application sends, so it's harder to exploit, but the impact is typically greater. In Azure, the nodes don't have permissions by default. These get added as you add integrations to your cluster. And same, you need the specific header. So with the same application as before, if I exploit this server-side request forgery, I can only control the URL, but not the headers, so I get back bad request. So again, where we are, we compromised some credentials from the worker node, right? Which means in AWS that if we authenticate as the worker node role, in AWS, we can, by design, authenticate to the cluster as a node too. And you can see it here. If I just do kubectl who am I, it tells me, well, you're a node now. So what can we do from there? And in EKS specifically, and that's not going to work for GKE or AKS, you can do some things. So one interesting thing to look is that system node has, in theory, a privileged cluster role. So if you look at the system node cluster role, it can like create pods, for instance. But in reality, that doesn't work because it's controlled by the node restriction, which tells you like, hey, don't do that. So in theory, it works. In practice, it doesn't. But there are a few things that we can do. The most interesting one being creating service account tokens. So let's take a step back. I'm a node. I need to run pods, right? And to run pods, I need to give them service account tokens. So by design, the kubelet authenticated as the node can create service account tokens and pass that to the pod, which means that we are authenticated as a node. We can do that. And really, the attack, again, is we are authenticated as a node. We say, hey, create a token for pod B for me. We get it back. So now we are authenticated as pod B, which maybe has other kinds of permissions. And then, well, we escalated our privileges again. So let's do just that. So let me clear that a little bit. So I'm authenticated as the node, same as before, using the credentials that we stole together. If we do kubectl run a specific pod, we'll see that it doesn't work. As I said, because we don't have all these permissions. I cannot get the secrets either. Now, if we try to create a service account token, we can do, so this looks a bit scary, but in reality it's just saying, I want a service account token for this pod. This is, for this service account. That's the name of the pod. That's the pod UID, which we can find from the pod definition, and put that into this file token. Okay, looks like this works. So if we look there, we see that we have a JSON web token that we can decode to see a little bit better. And we see indeed it's a GWT that is for the inventory service account, which, by the way, I forgot to show it, but we can just list all the pods. So once we have this, what can we do? Well, first thing to do is, who am I? Like, can I actually use this token to do anything against the API server? So I'm passing this to the kubectl who am I, and it's telling me, hey, now you are inventory service SA. Great. So if I do kubectl hot, what can I do? So this is a kubectl command that allows me to ask, give me all the permissions I have. I can see in that case that I was able to compromise a service account that has admin permissions. And I can not only list that, but I can also do it. So if I do kubectl get secrets with that token and put that as YAML in all the namespaces, this time it's going to work, which shows that I was able to escalate my privileges. As a summary, and I'm going to brief a little bit, so two types of vulnerability that we can exploit: server-side request forgery, remote code execution. It allows us to steal the worker node's AWS credentials from the instance metadata service. And from there, we can first pivot to AWS, which allows us to do some interesting things. But also, we can try to create service account tokens for any pod on the node. And with that, we can authenticate as this service account against the API server and potentially escalate our way or do all sorts of different things. This is especially true considering that nowadays there are a lot of daemon sets, things that have to run as privileged. So typically, you often have some interesting service accounts there. A few words around protecting against server-side request forgeries. I'd love to tell you, like, there's this thing, do it, it's going to keep you safe. I spent a few hours looking for a Java library to use URLs in a safe way, but nothing exists. So if you have some time, feel free to create one. There is one for Ruby, for Go, and for Node. So ideally, if you can, the best is to do some allow listing. If you know that your application only has to call specific IPs or host names, that's the best. Otherwise, you have to add a layer of defense at the cloud level. So on AWS, you have to enforce something that's called IMDS v2, which essentially requires you to add a specific header to call the IMDS and mitigate this risk. In Azure and Google Cloud, as we saw, you have to specify a header, so it's harder to exploit. Great, but this is actually not the main issue, right? What we want is we want to make sure that the pods cannot access the host's IMDS, because they shouldn't do that, right? The IMDS was meant to be used by the host. It contains host credentials, so the pods should not be able to access it. And that's really the root cause of the issue, right? Because if I can run arbitrary commands in the pod, like in this example, I can just provide the header that the IMDS wants. So this is not going to solve the root cause of the issue. So again, what we need to do is block the IMDS access from the pods. Good news is it's quite easy. So in GKE, you need to turn on GKE workload identity. I won't get into too much detail, but basically, when your pods make a request to 169.254, there's a daemon set on the node that intercepts this request using IP tables, and then it's going to make sure that you get back some properly scoped credentials. On AWS, I've read a few times that if you turn on IAM roles for service accounts or EKS pod identity, it's enough, but it's not, because it just gives you a new way of getting some credentials, but you still need to block access to the IMDS. So there are two things to do here, using a network policy to block it, and enforcing IMDS v2 with this setting that's called the response hop limit to 1, which means that you can still call the IMDS from the host, but not from the pods. And for Azure, it's the same. You need to block it with a network policy. There is something called Entra ID workload identity, but it's not enough to turn it on. So summary for this section, and then we'll have a few more things. SSRF is a major vulnerability, but specifically in the cloud is very impactful. And we did some research a few years ago, and we showed that it was actually responsible for a lot of documented data breaches in the cloud. So it's not really only something, in our mind, it's actually something that matters. And the second thing is that blocking pod access to the IMDS will protect these pivots in many cases. Now, we saw two kinds of vulnerabilities, remote code execution and server-side request forgery. There is another one I want to talk about, which I think is interesting, is what if we can read a single file from the application? And this is called local file read vulnerability, often called also path traversal. It's quite popular as well. It's probably older than me. Tens of years ago, with PHP, you had these already. And the idea is that you have an application that lets you read files and doesn't validate properly the input. So for instance, here I have an application that allows me to read files from TMP files, but if I do TMP files ... etc password, it will print etc password. Which means that in the context of EKS, I can print the service account token from the pod, which is mounted on this path. And from there, I can I can pivot, which is using this API call from AWS, which allows you to trade Kubernetes service account tokens for AWS credentials if your pod needs access to AWS. So let's have a look at this. So this is my application. It's vulnerable, so I can read files here. If I do etc password, I cannot do it, but again, if I do ... etc password, it works, so I can just do I can get the service account token here. So let me just put that into a file. I'm using Nano, not Vim, sorry. And then what I can do here is I want to use STS get color identity, but for that, I need the role that the pod is using. So how can I know that? Well, I cannot really. Nicely, there is a magic file that exists everywhere if you want to check on your laptop, which is called proc self environ, which contains the environment variables of the current process. So using this vulnerability, I can just go, oh, okay, here it is. This is the role ARN that I need. And then I can just do AWS STS assume role with web identity, giving it the role that I just found. And this is just giving it the token that we stole. And from there, we are able to get AWS credentials that were configured for this pod. So what did we just do? Again, this works if you can read arbitrary files, but also if you can execute commands in the pod, obviously. So stealing service account tokens from the pod file system, authenticating as the pod service account against the API. And maybe you're already a cluster admin, right? Maybe you're lucky. Otherwise, you can trade these credentials for cloud credentials and pivot to the cloud environment. That's for AWS. It's actually very similar for other clouds. It's just less documented. So for Google Cloud, you have an undocumented API that allows you to exchange Kubernetes service account tokens for GCP credentials. It's this URL. There's an obscure project on GitHub that uses it. It's not documented anywhere. And on Azure, it's actually a classic OAuth2 flow, same as all the other ones with specific parameters that you can find out quite easily as well. Which means that if we have a service account token and the pod was configured to use cloud credentials, well, we can use these as well in other clouds to get cloud credentials. To wrap up a little bit, so this is our complete attack flows that we saw today. You start from an application level vulnerability on the left, and you have different ways of going to the cloud, going back to the cluster, and doing this dance a few times to try to either escalate your way in the cluster, either find interesting things in the cloud account. A few things to keep in mind, and this is like the checklist for today. First thing is on EKS, make sure that you enforce IMDS v2 on all the worker nodes. This is now something that you can control by default. Since a few months, you can turn that on at the account level or at the IMI level, but it's really worth it. And on the others, in any case, you need to restrict pod access to the IMDS. And finally, it's interesting to know, when you have workloads in Kubernetes, what can they do in your cloud? Because that's super important to understand what pivot points you have. The problem with that is that it's actually very painful to do. So this is a picture of me trying to look at my service account tokens and my IAM roles policies to figure out what can do what. So last year for KubeCon, we released an open source tool that's called the Managed Kubernetes Auditing Toolkit, which is helping with these things. So first thing it does is you run it. It can look at your service accounts and your IAM roles in AWS and tell you, okay, given the configuration of these both things, I can see that this pod can assume this specific role. And it supports EKS pod identity, which was released a few months ago, and the classic IAM roles for service accounts feature. The second thing it helps you to do is to find hard-coded cloud secrets in your clusters. So specifically for AWS, it looks at config maps, secrets, and pod definitions and try to find these in a somewhat clever way to minimize false positives. And lastly, when you have blocked IMDS access to your pods because you went to vStock, you can run it to check that what you did is indeed working, and it will try to spin up a pod to curl the metadata service and make sure that what you did is working. If you want to use it, it's a single binary, very easy to set up, very easy to install, so feel free to contribute or to give some feedback. We are hoping to roll out a version for GKE as well. A few more resources before we close. So we have a Security Labs blog, which is essentially non-marketing security research. And we have a few write-ups on EKS that are a bit more exhaustive. So we have one on EKS, and we have one on specific features of EKS that were rolled out in late 2023, which is interesting for defenders, but also if you want to understand the attack vectors. And finally, a few weeks ago, I gave this talk at KubeCon. Sorry, it's a bit clickbait, but keeping hackers out of your clusters with these 5 simple tricks. So if you want to read either the article or look at the slides, feel free, and the link is there. Thanks a lot. The slides are available here, and this is my Twitter and my Mastodon. Thank you.
Are there any questions?
Thank you for the very, very nice talk. Just one question, maybe it's too simplistic, but would a web application firewall protect you from the SSRFs? And so you don't let your app call out to your attack?
So it's a great question, but very often the apps that are vulnerable, they have a legitimate feature, like an app that allows you to preview some images or to do webhooks. So very often you cannot just block the egress traffic. That says WAF can help in trying to block like SSRF payloads, but very often they can be bypassed. So I think WAFs are more about how can you make it harder for the attacker, and eventually, most of the time, you'll be able to bypass it. Yeah.
Thanks.
AWS introduced yet another way to call AWS API from Kubernetes clusters. It's AKS pod identity, I think. It looks much simpler, and it's much simpler to set it up. It doesn't do this trick with exchanging Kubernetes token to OIDC token. Have you checked this one? Is it also vulnerable?
Yeah, so in the tool that I showed, we do check for EKS pod identity. So if you have, for instance, this pod Kafka reducer that has EKS pod identity set up for this role, you will see that. In terms of the flow, actually, under the hood, it does exactly the same, but they abstract it away by running a daemon set that does that. And in terms of attack vectors, it means that if you are inside the pod that uses EKS identity, you can just try to do the same flow. But you have to be on the pod because you need to call some kind of link local address with the service account token. So it's an attack vector that requires, I think, remote code execution. Yeah.
Any more questions?
And by the way, if you're interested, I linked to a write-up on this feature that explains a bit how it's implemented under the hood.
Okay. So thank you very much, Christophe. And I think another round of applause is due.